Hi there, let's deal with topic 3, which is looking at spectroscopes and how we might use spectral analysis on stars and other celestial bodies to figure out their identity and their chemical makeup. This is a spectroscope. We have them in the school and we'll play with them. So kind of a black triangular thing here, and it has slits for light to enter. And so if we take white light and we look at it under the spectro, it'll have little slits which are called diffraction gradients, and it will cause light to slow down, bend, and create almost the colors of the rainbow in our eye. So spectroscopy works something like this. We know that pure white light will produce a full spectrum when it travels at a certain angle through a prism. And that full spectrum is the colors of the rainbow, which make up visible light. If you take all the colors of the rainbow, that's what makes up white light. And so when the makeup of white light is bent or slowed down or refracted, it will produce these colors. However, if something blocks it, you can get absorption lines, which are black, that interrupt the color of the rainbow, and we can possibly figure out what the identity of the substance was that did this. And so here's how spectrum lines work. Again, if we take white light from an incandescent bulb, we let it go through a diffraction slit or a hole so it's more in a linear format, and then it bends, we create the colors of the rainbow on a screen. But if it's not white light, if it's some other source of energy, then watch what can happen. So heated hydrogen through a diffraction and then allowed through a prism, it can create kind of an individual fingerprint, which we call the bright line spectrum. So hydrogen would produce this, which would give it, like I said, an identity. We know that hydrogen will produce these colors of lines when they are refracted. Whereas if we had superheated sodium, it would give off a spectrum, a bright line spectrum like this. Helium looks like this for its fingerprint. Neon and mercury would behave this way. Besides the continuous spectrum, which is the colors of the rainbow, there are absorption or dark line spectrums. And so here's how this works. A heated gas is allowed to pass through cooler gas and then through a prism, and dark lines, black lines here, which absorb, give us the identity of what happened there. For example, we can do this with sodium, and sodium looks like this. It leaves a fingerprint on the colors of the rainbow or the continuous spectrum, showing that sodium will absorb this particular area on the yellow. So this is just a review again of the different types of spectrum. So a continuous spectrum, we know from white light, shows up perfectly like the colors of the rainbow. We've talked about bright line spectrum, and there's also absorption spectrum, which leave black lines indicating whatever the substance was has blocked out the colors of the rainbow. So here's a spectroscope, and if we take different types of light and we look through the spectroscope, we might see different patterns that exist. Astronomers will put spectroscopes on their telescopes, and they will look out into the dark sky, and they will get different colors or patterns depending on the nature and makeup of the star. Some will have more helium or hydrogen, some might have a little sodium, etc. Here's our sun and the spectrum it produces when we use a spectroscope, and we can identify the various makeup. So let's look at that. Here's our sun. This is called an absorption spectrum, as opposed to the continuous colors of the rainbow, which is a continuous spectrum, or the other one is the bright line spectrum. So the black indicates that it's absorbed certain patterns, and therefore we can identify what's in our sun. So let's consider several types of elements: hydrogen, helium, sodium, and calcium, to see whether that is present in our sun. To do that, we simply take the fingerprint for hydrogen, one black line here, 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 and here, and we go down to the sun and we see if that is present. And so, same with helium. We can go down and see that, oh, there's one, there's kind of another. It doesn't quite line up, but close. There's the other one. There's this one. So helium looks present. How about sodium? No. As you can see, all these lines are not all present. Look at all these in sodium. Is that present there in our sun? No. How about calcium? Does our sun have any calcium? No. A lot of these lines, look at that one. That doesn't show up on the sun. So helium and hydrogen are the only substances on this that would show up in our sun. Next, I want to talk about how stars might be moving away from us or towards us. We have a phenomenon in physics called the Doppler effect. So the Doppler effect has to do with how waves travel, whether that's sound waves or some other wave like on the electromagnetic spectrum, light, etc. So if this person here and this person here are standing still and they hear a fire truck, and the fire truck's also standing still, the speed at which observer A and B hears the waves and how they sound are going to be equal. However, if the fire truck is driving towards observer A, the Doppler effect indicates that these sound waves are going to be compressed because they're moving towards you, and these ones are going to be stretched out and look slightly shifted because they're moving away from this person. Light waves work the same way. A star that's giving off some sort of electromagnetic radiation, if it's coming towards the Earth, it'll have a shorter wavelength, which means that it'll be blue shifted more to the left on our absorption spectrum. And if a star is moving away from us, according to the Doppler effect, its spectral lines will be slightly shifted towards the red colors on the spectrum. So they won't quite line up. Okay, so here's spectrum A. This is all the spectral lines present in a star. And then someone records from a telescope what they see about the stars one day, and what did they notice? Well, here's this double line. It kind of looks like this, except it's all been moved to the left. These lines are all four lines are present here in this star, but they've been shifted over towards the left or towards the blue side. We call that a blue shift, which means it still has the identity, the makeup of whatever is here, whether that's hydrogen and helium, but the second thing we know besides the makeup, we also know that this star is moving towards the Earth because the lines have been blue shifted. Here's the same star, but this time Here's the lines. Oh, they're here. They just hasn't lined up perfectly. If they lined up perfectly, that would mean the star is stationary. But they're just slightly shifted over towards the right. We call that red shifted, and that means that the star is moving away from the Earth. Okay, let's analyze 3 stars, A, B, and C, to see what's in them and to see whether they're moving, stationary, or not. So, star A, any hydrogen in star A? It doesn't seem, it might be this one. Might be that one. And, oops, I gotta go way down here. So, it might be that one. It might be this one. And it might be that. It just doesn't quite line up. That's there. That's gone a little bit that way, and that's gone a little bit that way. So there might be hydrogen, it's just it might be red shifted. Let's check, is there any sodium? No, no double line sodium. How about mercury? Maybe that one. Maybe that one. Maybe that one, just doubled up. And maybe that one, but it just came off. So what's our possible prediction about star A? Star A probably has hydrogen, and it probably has mercury, which is Hg. It's just that it's been red shifted, which means red shifted means that this star is moving away from us, from Earth. Let's check star B, star B. That one. That one. That one. Wow, they almost line up perfectly with the hydrogen. So we might say star B has hydrogen and it's stationary because those spectral lines line up almost perfectly. How about star C? Maybe hydrogen. There's that one. There's that one. There's that double for sodium. So sodium, for sure, just a little blue shifted. How about mercury? Maybe the mercury. I don't think hydrogen's there. My prognosis is it's sodium and mercury, and it's blue shifted or shifted more towards this way, which means it's moving towards the Earth. Blue shifted means it's moving towards the Earth for star C. Let's look at this again. Let's look at star A, B, and C. Actually, let's leave that. So that's just a good example of how spectral analysis might help us.